All right, let's dive into this really fascinating world where engineers are basically becoming doctors, but for the massive engines that power global trade. We're talking about a huge shift from just fixing things when they break to actually predicting the future, all thanks to some incredible tech and, you guessed it, artificial intelligence.
For decades, the old way of doing things was, well, pretty simple. You just wait for something to break, and then you'd scramble to fix it. It was a high-risk, super high-cost game of whack-a-mole. But today, we're in a whole new era of what's called predictive maintenance. The goal isn't just to react anymore, it's to prevent failure completely by fixing things before they can break. And that means less downtime, way lower costs, and much, much safer ships. So how do you even make a shift that big? Well, the core idea is actually simple, but it's incredibly powerful. You start treating the machinery like a patient. Instead of waiting for a total catastrophe, you perform regular checkups to catch any little problem super early. This is exactly how we move from constant breakdowns to real breakthroughs.
Now, there's a formal name for this whole strategy, and it's called condition-based maintenance, or CBM. The idea is all about using real-time data from special monitoring tools to decide when maintenance is actually needed. So no more guesswork, no more random schedules. You only step in when the machine's own condition tells you it's time.
And this right here, this PF curve, it shows you exactly why catching things early is so critical. See that point P? That's where a potential failure just begins, but it's totally silent, completely invisible. Only sophisticated tools like vibration analysis can even hear it. As you move along the curve, other signs, like heat, might start to show up. But by the time you can actually hear a problem with your own ears, you're way down the line, and you're probably looking at serious damage. The whole goal of CBM is to find that problem way back near point P. And listen, this isn't just some theory from a textbook. People in the field, like Electrical Superintendent Klaus von Glahn, are seeing the impact firsthand. He says that following this system doesn't just cut down on paperwork and workload for his engineers, it fundamentally improves the reliability and, most importantly, the safety of the machines they all depend on.
So, if we're calling these engineers machine doctors, what's in their medical bag? What are the instruments in their digital toolbox? How are they giving a checkup to a gigantic ship engine? Let's take a look at 3 of the key technologies that make all this possible. First up, you've got the stethoscope of the engine room, vibration monitoring. You see, every single rotating machine has its own unique vibration signature when it's running healthy. It's kind of like a fingerprint or a heartbeat. By listening for the tiniest, most subtle changes in that signature, engineers can pick up on these hidden tremors that signal trouble way before any other symptoms show up. And the way they collect this data is super systematic. It's not just random. An engineer will download a pre-planned route of all the measurement points onto a handheld device. Then they physically walk that route, taking readings from each machine, before uploading it all back to a computer. This really structured process is what ensures the data is consistent and comparable over time, which is absolutely crucial for getting an accurate diagnosis. Okay, next tool in the box is the thermometer, or, in this case, thermal imaging. Using a special infrared camera, engineers can literally see heat patterns that are invisible to the naked eye. This lets them spot all kinds of hidden problems, like a loose electrical connection, an overloaded circuit, or a bearing that's about to fail, long before it can cause a fire or a major breakdown. And this is so cool. This shows how that data gets turned directly into action. It's not just about, hey, that spot looks hot. It's about quantifying the risk. So, a temperature rise of just a few degrees might just warrant an investigation. But a spike of over 40 degrees Celsius, that's a critical alert. That means stop what you're doing and repair this immediately. And finally, of course, what's a checkup without a blood test? Well, for a machine, that's lube oil analysis. The oil flowing through an engine is basically its lifeblood, and by taking just a small sample and analyzing it for contaminants, or changes in its properties, or even tiny metal particles from wear and tear, you can get this incredibly detailed picture of the machine's internal health. Okay, so you're collecting all this amazing data, vibrations, temperatures, oil reports. That's one thing. But making sense of it all? Seeing the patterns hidden across thousands of data points from hundreds of different machines? Whew, that requires a much, much bigger brain. And this is exactly where artificial intelligence comes into the picture. So let's talk about the AI brain behind this whole operation. Let's see how this whole thing builds from just a simple monitoring system into something that is truly predictive. We're talking about turning mountains of raw data into smart, forward-looking decisions. The framework for this AI brain has a name. It's called Prognostic and Health Management, or PHM for short. And it's an entire system designed not just to see what's happening right now, but to use all that data to diagnose problems, predict what's going to happen next, and even recommend the absolute best thing to do about it.
PHM basically works in 4 logical steps, and it's a lot like a visit to the doctor. First, it monitors the patient's vital signs to see if anything looks off. If it spots an anomaly, it moves to diagnosis, trying to figure out what's wrong and how bad it is. Then comes the magic part, prognosis. This is where it actually predicts how the problem is going to develop over time. And finally, you have health management, where it basically writes a prescription for the best treatment plan.
Now, I've got to say, the most powerful, most revolutionary part of PHM is that prognosis step. This is where the system stops being just a doctor and starts to feel more like a crystal ball, giving engineers this incredible ability to see into the future of a machine's health.
So how on earth does it do that? Well, AI models, especially deep learning models, they go to school. They study vast amounts of historical data from other machines that were run all the way until they failed. By poring over these past breakdowns, the AI learns to recognize the incredibly subtle, complex patterns in sensor data that are the telltale signs of a failure that's about to happen. And the AI's output isn't some vague warning like, hey, you might want to check this out. No way. It gives a specific, actionable number, the remaining useful life, or RUL. It's literally telling the engineers, okay, based on everything I'm seeing, this specific bearing has about 150 hours of operation left before it's going to fail. Deep learning is just so good at this because it can attack the problem from all of these different angles. It can automatically find those complex patterns over time that a human analyst might never, ever spot. It can use something called transfer learning to take what it learned from one engine and apply it to another. It can even model uncertainty, giving you a probability range, not just one number, to help you manage risk. And it pulls together data from all the different sensors to create one single, holistic picture of the machine's health. Now, of course, this all sounds pretty amazing, but it is not simple. Making these systems work in the real world is incredibly complex, and there are some pretty major challenges, both practical hurdles in the engine room and some really tough theoretical ones back in the research lab. On the ship itself, engineers are dealing with very real problems. First off, all this monitoring gear is expensive. The crew also needs a lot of specialized training to use it right and to understand the data. Plus, a ship's engine room is a brutal environment. Salt, heat, constant vibration. It can destroy sensitive electronics. And on top of all that, some types of failure like metal fatigue just don't give off clear warning signs for these tools to pick up. Meanwhile, back in the research labs, the AI scientists are wrestling with their own set of tough problems. Like, how do you make a model that you trained on engine A work just as well on engine B, which is slightly different? Here's a weird one. Failures are rare, which is great, but it makes it really hard for the AI to get enough bad examples to learn from. And how do you teach the AI to hear that one tiny fault signature through all the background noise and chaos of a massive working ship?
And all of this brings us to one last really crucial question. As these incredible predictive systems get smarter and more autonomous, what's the future role for human experience and intuition? In a world that's flooded with predictive data, how do we make sure that the seasoned chief engineer, the human expert with decades of wisdom, always remains at the helm?